starting, all those who have written their names in chat before this moment, please repeat it, do it once again, because only those names which were written during record will remain when the record is complete, so they will be saved as a separate text file. Well, and now let us start studying physics.
Que ahora para saber cuál es el nombre del profesor.
I think I will need to mute your microphones from time to time. And here is my lecture. As I said, we'll start with physics, and I'll tell something about organization of process in the end. So today's general topic is electricity, and we'll discuss some fundamental things related to this topic, and then we'll discuss some application of electricity in medicine. Of course, there are many others, but we'll discuss only electrocardiography, ECG, and something related to appearance of electric signal in this process. And we'll start with very fundamental thing. It is a Coulomb's law. It is the law of interaction of 2-point charges. You know that electricity was known by human from very old times. It was known that some small objects can be attracted to each other if they were in contact with some other objects. This process is called neutralization, but it was not a systematic fundamental study of this phenomenon before the end of 18th century. Most of physics was started in the 17th century with the works of Newton and Galilei, but in the next century people become to study electric phenomena, and one of the first scientific law found in this field was in Coulomb's law. He studied the dependence of force of interaction between two small charged particles, and he found that this force is directly proportional to the charge of each particle, and it is inversely proportional to the squared distance between the particle. So we can write this law in terms of equation 1. In scalar form, it looks like F equal to K Q1 Q2 divided by R squared, where I is distance between point particles, point charges, Q1 and Q2 are charges, and K is coefficient of proportionality. It depends on the unit of measurements for electric charges. There are two basic unit system used in physics now. It is SI system international, and SGS, I'm sorry. centimeter gram second. In contrast to SI system, the charge is not measured in coulombs, it is measured in units of charge for SGS system. And the difference between these two systems is that in SGS, this coefficient K equals 1. So the charge has the dimension which can be found from this equation. Newtons divided, newtons multiplied on R squared, and then we can take a square root of this value. And this system is not used widely in everyday life. In everyday life, we measure charge in coulombs, we measure voltage in volts and current in amperes. But SGS system is widely used in theoretical physics because it is useful there. It is useful because the vectors of electromagnetic field has the same. In SI system, this coefficient K is represented in terms of electric constant. We'll probably discuss it later. So anyway, the most important thing in this equation is not coefficient K, of course, it is the dependence of force on distance on R. And, initially, it was found by Coulomb that this force inversely proportional to R squared. And now this power, the exponent of R, is measured with very high precision, and it is shown that this exponent is equal to with the precision of 10 to the power minus 16, so very, very high. It means that the Coulomb's law satisfies some assumption about the symmetry of space and time, which can be made based on this dependence. And these assumptions are proved to be correct with the very high precision. One more thing here is vector form of the Coulomb's law. We know that force is the vector quantity. It is characterized by its value and by its direction. So the force can be written as a vector, and it can be done using the vector R12, which connects first charge and second charge. Using this vector, we can represent the force in terms of this equation. One can see that power is 3 in denominator now, but it doesn't mean that force is inversely proportional to cube of radius, because we have some radius in to power 1 in numerator, but it is not only the absolute value, it is vector R12. Well, let us see the next page, and here we can introduce first the electric field. So the Coulomb's law was the law of interaction between two particles, and it does not require to the introduction of the new type of material, which is called field, but it becomes more simple for application if we introduce a new physical quantity. we can see that the force is always proportional to the charge. That's why we can say that the first charge produces electric field, and this field acts on the second charge. In this case, the force will be always proportional to charge and field. Now we can introduce new physical quantity, electric field E. It is introduced by equation 2, which is equal to the force acting on a test charge divided by the value of this test charge. And we assume that electric field exists independently of presence of charge. So we assume that there is a new type of material, and at any given point of space is characterized by the value of electric field. If we put a test charge inside this point, we can see that the charge exerts, it is under the action of some force given by equation 2. Well, if we had only the Coulomb's law, the electric field would be just a useful method of calculating force. But you probably know that there are some other equations of electric and magnetic field which relates those fields to one to another, and from those equations there is a sequence that electric and magnetic fields can form a wave, electromagnetic wave, which exists without the source of which have produced it. So, for example, if we have some antenna which creates electromagnetic wave, the wave goes away from antenna and it exists even if the antenna disappeared. So this phenomenon is the manifestation of the fact that electromagnetic field is a new type of material which exists, which can exist without charges which created this type of material. Well, so today we are studying only electric field, and it is characterized by vector E. Another way to characterize it is using the potential, which is based on energy. But before this, let us consider the space distribution of electric field produced by a point charge Q. According to the Coulomb's law, this electric field is inversely proportional to the distance from charge and is given by equation 3 or by equation by the same equation in vector form. The electric field can be represented by the lines which the lines of electric field which are characterized by the direction of the tangential line, and this tangential line is it coincides with the direction of electric field in every point. For the case of point charge, the shape of these electric lines are very similar. They start at the point charge if it is positive and goes to infinity as straight lines. And if the charge is negative, they start at infinity and goes to the point where the negative charge is. So the picture is simple. A very important property of electric field is the superposition principle. It was found in experiments. It was found in experiments with several charges which acts on one test charge. If we have several charges, then the force produced by them is just a vector sum of all forces which would be produced if we had only one charge independently of others. So in terms of electric field, this superposition principle can be formulated as equation 4. So the total electric field is a vector sum of all fields produced by all sources of electric field. In case of point particles, E sub I is electric field created by I's point charge. Well, please wait a second, I'll close the curtain. Well, I'm here again, and now let's just go further. So another way to characterize electric field is to using its energetic characteristics. So we can discuss not only force produced by electric fields, but we can discuss the work done by electric fields forces. And it is interesting that this work does not depend on the trajectory of particle. It is characterized only by initial and final points in space. The fields for which it is valid are called potential fields. And not every field is potential. There is some mathematical criteria which allows one to find if the field is potential or not. But the field produced by a point particle is potential because it depends only on distance from the particle, and it is directed in the direction of radius vector. Those fields are called radial, and all the radial fields are potential fields. The work done by the forces does not depend on trajectory. It depends on the initial and final points. And if this property is valid for the field, we can represent the work as a change of some potential function u. So we can introduce new function of radius vector, which is called phi, and which is called electric potential. It is denoted as phi and is called electric potential. And the work done by electric field equals to charge multiplied on difference of electric potentials between 2 points. The definition of phi is equation 5. So the change of the potential between two close points is equal by equation 5. And dr here is infinitesimal change of radius vector r, or displacement vector of particle. Using this definition of electric potential phi, we can calculate the electric potential for a point charge. and it can be found by integration, and it gives us the equation 6, which looks similar to equation for electric fields. Let us go back and look at the equation 3 for electric field. So the electric field is inversely proportional to R squared and directly proportional to Q. The electric potential phi is inversely proportional to R to the power 1. So the difference between the equation for E and phi is the power of R in case of phi, which is minus 1. Another difference is that phi is a scalar quantity. It characterizes scalar quantity work done by electric forces. And in contrast to E, we do not need another form of this equation. So phi can be given by equation 6. And one important thing concerning phi, our definition is based on equation 5, and in this equation we have defined d phi, so change of potential. It means that if we add some constant to phi, the definition will remain the same. And it means that the potential is defined with the precision of some constant value. So we can add some constant to equation 6, for example, and all the forces will be the same, all the work done by electric field will be the same. So we need some rule how to find this constant quantity which can be added to equation 6. And the usual rule is that we assume that phi tends to 0 when r distance tends to infinity. It is it makes sense because at infinity there is no interaction between two particles. That's why it is it would be good to say that phi equals 0 at infinity. Well, next thing, which is not as fundamental as we discussed before, but which is important from the point of view of application to medicine, is a term electric dipole. Electric dipole is some electric dipole moment. P is some vector characteristics which describes the properties of a system which has total charge equals 0. So at large distances from many objects, the shape and the size of objects becomes less and less important. The larger the distance, the less important size and shape. So from the large distances, many objects can be considered as point particles. And the same is true for electric fields produced by them. So from the large distances, any electric systems looks like a point particle. And it means the fields produced by any systems on long distances can be found by the equations for point particles. But if the total charge of the system is equal to 0, then we would have 0 electric field on long distances. And it is not always true. the electric fields can be non-zero if the distribution of positive and negative charges are different. Then at large distances from the object, we can characterize its electric field by some vector value, which is called electric dipole moment. Let us first consider the simplest electric system, which is characterized by electric dipole moment. It is 2 point charges separated by some distance d. And the charges are of different sign, plus q and minus q. So the electric dipole moment of this system is defined by equation 7, P equals Q D, where D is displacement vector. And it points from the negative charge to the positive charge. Well, let us see how the electric field of this dipole, this point dipole, looks at large distances. If we draw the lines of electric fields for the case of 2 point charges, we will see the picture like this. So the lines start at the positive charge and goes and ends in the negative charge. So this is the picture of electric field for some electric dipole, which is not very small. We do not look from on this system from very large distances. But if we enlarge distance and look from farther and farther points, we will see this distance between minus and plus q becoming smaller and smaller. So we will come to the system which is called point electric dipole. This system is simply from the theoretical point of view, because the field created by this point dipole is it can be found in terms of equation 8, and this can be represented as seen on this picture. So we don't see the area where electric field is now directed in directions in opposite direction to the electric dipole moment between the charges plus and minus. You can see that electric field is directed from plus to minus, but in case of electric dipole, in case of point electric dipole, this area becomes invisible, and the picture looks like this. It is characterized by equation 8, and we can see that we have r to power 5 in denominator and r to power 2 in numerator. In this case, it is scalar r to power 2. In this term, we have two scalar product of p and r. Then it is again multiplied on vector r. So the absolute value depends on r as r squared. And it gives us the dependence on distance as inversely proportional to cube of r. So it decreases with distance quicker than the field of point charge. That field decreased with inversely proportional to r squared. The field of point dipole decrease inversely proportional to cube of r. And if we had some non-zero charge of the system, then at some distance the term of electric fields produced by its charge will be larger than the fields produced by its dipole moment. But in case of total zero charge, we have only this term. So we should take this, we should find the fields by this equation. And this object, I mean the electric dipole, is important from the point of view of application to electric cardiography. You see that almost every organ in our body is a complicated system from the many points of view. And our heart, which produces some electric field, is again an complicated object. So it is not a point particle, it is not a point dipole. But if we will describe its field very detailed, it would be difficult to analyze these. That's why in the theory of ECG, the human heart is considered as a point electric dipole. It allows one to simplify the analysis of data. And this simplification is enough for diagnostic properties, and it is very important from the possibility to understand. Because if we discussed the real fields, it would be very complicated, and we were unable to make some diagnostical conclusions based on this a lot of data. We use simplified model instead of this. Well, let us go to the next slide. So here we can see not the distribution of electric field strengths, but the distribution of electric field potential. The potential produced by a point electric dipole can be found from equation 9. It is simpler than equation for electric field strength, the previous equation 8. So we can see the scalar product of vector P and vector R. P is electric dipole moment, R is radius vector. And the scalar product in the theory is a projection of one vector onto another. And if we consider the case of fixed distance from the electric dipole to the point of where we are finding the potential phi, so we assume we are on a sphere of the radius r. Then the absolute value of r in equation 9 will be fixed, and the potential will depend only on orientation of vector r relative to vector p. And the difference of potential in this case will be proportional to the scalar product of p onto the difference of radius vectors r1 and r2. So delta I equals r2 minus r1. And we can say that the potential difference is proportional to the projection of vector p onto vector delta r, or onto vector delta r onto vector p. But for our application, it's better to say it is proportional to projection of p onto delta r. That's why, so this equation is used in theory of ECG, where the potentials produced by electric charges in our heart are measured at 3 points of our body, and we have a triangle with 3 sides, and the potential difference on between 2 points, every 2 points of this triangle, is assumed to be proportional to the product to the projection of a vector p onto the given side of the uh, triangle and to the given line. And here is the picture of electric potential distribution. The color here is represented the sign. So on the right hand side it is positive, for example, on left hand side it is negative. And the intensity of color represents the intensity of potential. So the highest potential is at the position of positive charge, and the lowest potential is the position of negative charge. And again, this picture is not for point dipole, it is for dipole with some distance between charges plus q and minus q. If you want to get it for point dipole, we should make this distance d tend to 0. So these two areas will become close one to another, and they should form, they should coincide in the middle point. But it will give us strong changes in this region, but the field in outer regions will remain the same, and it will look similar. And wait a second, do I have a... Unfortunately, I don't have this picture here. Oh, no. Well, so let us compare this picture with the picture of electric field distribution. One can see that electric field is always perpendicular to the line of equal potential. So those lines here correspond to areas of equal potential. And if we compare this picture with that one, you can see that electric field is always perpendicular to the field of electric potential. So this allows one to draw the picture of electric field by the known picture of electric potential. For example, here one can start drawing the line which would be perpendicular to every line of equal potential, and we'll get the picture like this. Well, one more important thing concerning to the electricity is the equation which connects the, which relates the potential difference and current. So the current is phenomenon of transmission of charge inside some type of materials which are called conductors. There are some type of materials which are able to transmit charge because there are some charge carriers inside these materials which can travel from one point of the object to another. You probably know that the electric current can be transmitted by solid solid objects, and by liquids, and by gases in some cases. So in case of liquids and gases, the charge carriers are electrons and ions, In case of solid objects, only electrons can transmit the electric charge inside solid object. And there are different types of solid state. There are some materials which are called conductors, which can transmit electric current. Other materials are called insulators. They are unable to transmit electric current. And there is another type of materials which is called semiconductors, which can transmit the current, but the dependence of their resistance on temperature is different than for metal conductor. And for those two types, I mean conductors and semiconductors, there is a Ohm's law which says that current is directly proportional to voltage, to potential difference applied to the point of the conductor. And the coefficient of proportionality, which is in denominator in equation 11, is called resistance and is measured in ohms. So this law is called Ohm's law, which was found out in the beginning of 19th century. Actually, it's the difficulty which was in discovering of this law was the measurement of voltage independent of measuring of current. So this difficulty was overcome by George Ohm, and he found that current is directly proportional to voltage. If we discuss how fundamental this law is, we should say that it is not as fundamental as Coulomb's law, for example. So this law actually is based on the fact that voltages we deal with in our everyday life are too small compared to the voltages which could be characterized the atomic electric field. So if we want to characterize electric fields in atom in terms of some voltage, then it would be much larger than the voltage we can obtain in our experiments. That's why V is always small compared to some fundamental voltage. And that's why we have linear approximation. So the dependence of current on voltage could be non-linear, but since we are on the very beginning of this dependence, we can see that it always satisfies the equation 11. Well, and if we are discussing ECG, this is again important law for us because we are going to measure potential difference V, and we are going to measure it not in a free space, but in some conductive medium. So our body includes a lot of liquid, and this liquid can conduct electric fields. So our body is a conductor of electric field. Its resistance is large compared to resistance of metals, So we can call our body as a weakly conductive medium. And we can see from Ohm's law that current between 2 points in a conductive medium is proportional to the voltage distance, to the potential difference between these 2 points. And this is used in measurement of potentials produced by Hart in the ECG theory. Well, now let us discuss some biological terms related to the electric field. And if we discuss the electric fields produced by Hart, we should first discuss how electric potentials appear in our cells. So here is the slide describing the appearance of action potential. And I think that before we discuss these pictures, it would be better to watch some videos. So let me start a video from YouTube. Wait a second, probably this one. This is a simple video by some person, and it is very short, but it describes well the appearance of action potential.
Before a neuron can conduct an electrical signal, a resting membrane potential must be established, with a positive charge outside the cell and a negative charge inside the cell. One way the charges are established is by the presence of large negatively charged proteins within the cell. An active transport protein called sodium-potassium ATPase uses ATP to transport sodium out of the cell and potassium into the cell. The pump binds to 3 sodium ions. Then, using the energy from a molecule of ATP, the pump changes conformation. The sodium ions are released to the outside of the cell. The new shape of the channel has a high affinity for potassium. The binding of 2 potassium ions causes the channel to change conformation again. The pump releases the phosphate to the inside of the cell as well as the 2 potassium ions. The cycle continues when 3 more sodium ions bind to the channel along with another molecule of ATP. Many potassium leakage channels are located throughout the cell membrane. The sodium-potassium pump establishes an electrochemical gradient, and the potassium ions flow from the areas of high concentration inside the cell to areas of low concentration outside the cell. These processes establish the resting membrane potential. A typical cell will have a resting voltage of about negative 70 millivolts across the cell membrane.
Well, so in less than a few, than 2 minutes, this video described, let us see this one.
Incoming signals are received at membrane potential or membrane refers to the difference of electric charges across a cell membrane.
Let me stop the video for the moment and once again. So the previous video described appearance of a membrane potential. So the cell membrane contains some channels for sodium and potassium ions, and one of those channels uses energy of ATP, which is genazine phosphate acid. So this is a universal energy source for our body, ATP, and using this energy, the membrane can pump potassium ions outside, So each pumps sodium ions outside and potassium ions inside. So the total number of ions in one cycle is 3 outside and 2 inside. That's why we have negative charge inside. And this is dynamic process, so some of ions leave the cell through the channels. And normally, if the cell is alive, there is an equilibrium between the flow of ions inside and outside, and this equilibrium leads to formation of some potential. So let us look another video, which is a bit longer. It is at least for 4 minutes. It is more professional, but it does not include some important things which were in the previous one. So let's just see this one.
Membrane. Most cells have a negative transmembrane potential. Because membrane potential is defined relative to the exterior of the cell, the negative sign means the cell has more negative charges on the inside. There are 2 basic rules governing the movement of ions. They move from higher to lower concentration, just like any other molecules. Being charge-bearing particles, ions also move away from like charges and toward opposite charges. In the case of the cell membrane, there is a third factor that controls ion movement: the permeability of the membrane to different ions. Permeability is achieved by opening or closing passageways for specific ions, called ion channels. Permeability can change when the cell adopts a different physiological state. Consider this example. 2 solutions of different concentrations of sodium chloride are separated by a membrane. If the membrane is equally permeable to both sodium and chloride, both ions will diffuse from higher to lower concentration, and the 2 solutions will eventually have the same concentration. Note that the electric charges remain the same on both sides and membrane potential is 0. Now let's assume that the membrane is permeable only to the positively charged sodium ions, letting them flow down the concentration gradient while blocking the negatively charged chloride ions from crossing to the other side. This would result in one solution becoming increasingly positive and the other increasingly negative. Since opposite charges attract and like charges repel, positive sodium ions are now under influence of 2 forces. Diffusion force drives them in one direction, while electrostatic force drives them in the opposite direction. The equilibrium is reached when these 2 forces completely counteract, at which point the net movement of sodium is 0. Note that there is now a difference of electric charge across the membrane. There is also a concentration gradient of sodium. The 2 gradients are driving sodium in opposite directions with the exact same force. The voltage established at this point is called the equilibrium potential for sodium. It's the voltage required to maintain this particular concentration gradient and can be calculated as a function thereof. A typical resting neuron maintains unequal distributions of different ions across the cell membrane. These gradients are used to calculate their equilibrium potentials. The positive and negative signs represent the direction of membrane potential. Because sodium gradient is directed into the cell, its equilibrium potential must be positive to drive sodium out. Potassium has the reverse concentration gradient, hence negative equilibrium potential. Chloride has the same inward concentration direction as sodium, but because it's a negative charge, it requires a negative environment inside the cell to push it out. The resting membrane potential of a neuron is about negative 70 millivolts. Notice that only chloride has the equilibrium potential near this value. This means chloride is in equilibrium in resting neurons, while sodium and potassium are not. This is because there is an active transport to keep sodium and potassium out of equilibrium. This is carried out by the sodium-potassium pump, which constantly brings potassium in and pumps sodium out of the cell. The resulting resting potential, while costly to maintain, is essential to generation of action potentials when the cell is stimulated.
Well, so this video explained the process in more detailed way, but some things were missed here. It is the requirement to use energy and use ATP molecules for the operation of potassium sodium pump. Well, so we can come back to these pictures, and it was described in those two videos that the human cell are in some way charged objects. So they have negative charge inside and some positive charge in outside liquid. So this difference of charge lead to appearance of difference of voltages. Of course, the difference of charges is very, very small. So to obtain the voltage difference of 70 millivolts at such a small distances, we need a very small difference of charges. That's why we don't characterize the charged cells by the charge. The better quantity which characterizes the process is the membrane potential. And this membrane potential plays an important role in the process of cells activation. When our muscles are contracted or our heart is making its work, there is a nerve pulse which comes to the muscle, and it starts the muscle contraction, and it is traveled by the nerve tissue using this cell potential. Let us see one more video describing the appearance of action potential and describing the motion of the movement of nerve pulse.
Dendrites, while outgoing signals travel along the axon to the nerve terminal. In order to achieve rapid communication over its long axon, the neuron sends electrical signals from the cell's body to the nerve terminal along the axon. These are known as nerve impulses, or action potentials. An action potential is essentially a brief reversal of electric polarity across the cell membrane. Cells are polarized, meaning there is an electrical voltage across the cell membrane. In a resting neuron, the typical voltage, known as the resting membrane potential, is about -70 millivolts. The negative value means the cell is more negative on the inside. At this resting state, there are concentration gradients of sodium and potassium across the cell membrane. More sodium outside the cell and more potassium inside the cell. These gradients are maintained by the sodium-potassium pump, which constantly brings potassium in and pumps sodium out of the cell. A neuron is typically stimulated at dendrites, and the signals spread through the soma. Excitatory signals at dendrites open ligand-gated sodium channels and allow sodium to flow into the cell. This neutralizes some of the negative charge inside the cell and makes the membrane voltage less negative. This is known as depolarization, as the cell membrane becomes less polarized. The influx of sodium diffuses inside the neuron and produces a current that travels towards the axon hillock. If the summation of all input signals is excitatory and is strong enough when it reaches the axon hillock, an action potential is generated and travels down the axon to the nerve terminal. The axon hillock is also known as the cell's trigger zone, as this is where action potentials usually start. This is because action potentials are produced by voltage-gated ion channels that are most concentrated at the axon hillock. Voltage-gated ion channels are passageways for ions in and out of the cell, and as their name suggests, are regulated by membrane voltage. They open at some values of the membrane potential and close at others. For an action potential to be generated, the signal must be strong enough to bring the membrane voltage to a critical value called the threshold, typically about -55 millivolts. This is the minimum required to open voltage-gated ion channels. At threshold, sodium channels open quickly. Potassium channels also open, but do so more slowly. The initial effect is therefore due to sodium influx. As sodium ions rush into the cell, the inside of the cell becomes more positive, and this further depolarizes the cell membrane. The increasing voltage in turn causes even more sodium channels to open. This positive feedback continues until all the sodium channels are open and corresponds to the rising phase of the action potential. Note that the polarity across the cell membrane is now reversed. As the action potential nears its peak, sodium channels begin to close. By this time, the slow potassium channels are fully open. Potassium ions rush out of the cell, and the voltage quickly returns to its original resting value. This corresponds to the falling phase of the action potential. Note that sodium and potassium have now switched places across the membrane. As the potassium gates are also slow to close, potassium continues to leave the cell a little longer, resulting in a negative overshoot called hyperpolarization. The resting membrane potential is then slowly restored thanks to diffusion and the sodium-potassium pump. During and shortly after an action potential is generated, it is impossible or very difficult to stimulate that part of the membrane to fire again. This is known as the refractory period. The refractory period is divided into absolute refractory and relative refractory. The absolute refractory period lasts from the start of an action potential to the point the voltage first returns to the resting membrane value. During this time, the sodium channels are open and subsequently inactivated while closing and thus unable to respond to any new stimulation. The relative refractory period lasts until the end of hyperpolarization. During this time, some of the potassium channels are still open, making it difficult for the membrane to depolarize, and a much stronger signal is required to induce a new response. During an action potential, the sodium influx at a point on the axon spreads along the axon, depolarizing the adjacent patch of the membrane, generating a similar action potential in it. The sodium currents diffuse in both directions on the axon, but the refractory properties of ion channels ensure that action potential propagates only in one direction. This is because only the unfired patch of the axon can respond with an action potential. The part that has just fired is unresponsive until the action potential is safely out of range. An action potential generated at the axon hillock usually travels down the axon to the nerve terminal and not back to the cell body. This is because the concentrations of voltage-gated ion channels are higher in the axon than in the cell body.
Well, so we have seen this video, and it describes the propagation of nerve pulse. Here is another picture on this same theme, and we can see that in axon there is a wave of depolarization. It is important that during the period of repolarization, the axon becomes it becomes unsensible to another uh, polarization pulses, that's why the wave doesn't go back. So, for example, in this region, the charge on the right-hand side is positive, and the membrane is depolarized, and it could produce a wave going back through the nerve axon, but actually the wave doesn't go because in this region the axon is insensible, so it does not react on the wave. There is no polarization. It is not ready for transmitting of signal. That's why the nerve pulse goes only in one direction. Another important thing here is that the nerve pulse is not an electromagnetic wave. It is a wave of electric depolarization, and it includes the motion of ions, the chemical reactions, opening of some channels, closing of another channels, and that means the speed of the nerve pulse is not the speed of light. It is actually even slower than speed of sound. The speed of sound in the air is about 300 meters per second. In liquids, for example, in water, it is about 1000 meters per second. But the speed of nerve pulse is about 10 times smaller. It is about 100 meters per second. So it is enough for the for functioning of the body, for every part of the body operate in its due way. And anyway, it is not as quick as light, and of course is not as quick. Of course, it's not as quick as light, and even is not as quick as sound. So we should remember that it is not just an electromagnetic wave, it is the wave of electric polarization. Well, here is some text on action potential. I think we can skip this slide now because we have seen some video. It is one more picture describing the propagation of nerve pulse in nerve in axon. So we should remember that initially the cell is polarized and it is ready for transmitting of electric depolarization wave. So initial stage is look like this: more potassium inside, more sodium outside, and negative inside, because the number of sodium ions which went outside is larger than the number of potassium which comes inside. So the channels are opened by this stimulation. So depolarization stimulates the opening of channels, and this leads to appearance of wave of depolarization. It doesn't go back because on the back side we have the same charge distribution but different ion distributions. That's why on the back side the cell is not ready for transmission signal. If at the same potential the distribution of ions is different, the cell will not transmit this depolarization wave. Now it again explains the appearance of action potential. One more picture of text. And next topic is ECG. So we will discuss it very shortly because we are short in time now. So it was invented by Einthoven in the beginning of 20th century. Here he used an 3 buses with natrium chloride solutions as electrodes, because our skin is not a good conductor. It is mostly insulator, and to conduct the electric signal we need a large area of contact. In modern devices it is not so strictly required, because modern electric devices are much more sensitive. That's why they can sense a signal which is much lower, and it's enough the current which flows through some electrodes with the small area, much smaller areas than he used in his first experiments. But the idea remains the same. The idea is that we are finding the potentials obtained from 3 points of our body, and those potentials are created by heart. I think we have time for watching one more video. Let us see the next
The
video
heart's
on the
conduction
one.
system controls the generation and propagation of electrical signals, or action potentials, that cause the heart's muscles to contract and the heart to pump blood. This electrical activity can be measured at electrodes placed at specific points on the skin, from which a composite recording is produced in the form of a graph. This recording is known as an electrocardiogram, or ECG, sometimes referred to as an EKG. A tracing of the overall electrical activity of the heart, resulting from the propagation of many action potentials. Let's look at what happens during a single beat of the heart and how these events are depicted on an ECG. In a normal heart, each beat begins in the right atrium with an action potential signal from the sinoatrial or SA node, the heart's natural pacemaker. The signal spreads across both atria, causing the muscle cells to depolarize and contract, inducing a phase known as atrial systole. On the ECG, this atrial depolarization is represented by the P wave. The period of conduction that follows atrial systole and precedes the contraction of the ventricles is depicted on the ECG by the PR segment, a flat line following the P wave. When the signal leaves the atria, it enters the ventricles via the atrioventricular or AV node, located in the interatrial septum. It enters the bundle of His and spreads through the bundle branches and the large diameter Purkinje fibers along the ventricle walls. As the signal spreads through the ventricles, the contractile fibers depolarize and contract very rapidly, inducing ventricular systole. The ECG's QRS complex represents this rapid ventricular depolarization. Atrial repolarization also occurs at this time, but any atrial activity is hidden on the ECG by the QRS complex. Finally, as the signal passes out of the ventricles, the ventricular walls start to relax and recover, a state described as ventricular diastole. The dome-shaped T wave on the ECG marks this ventricular repolarization. On the ECG, the ST segment depicts the period when the ventricles are depolarized. The QT interval represents the time it takes for both depolarization and repolarization of the ventricles to occur. The sequence of events just described and the associated ECG trace repeats with every heartbeat. Remember, an ECG is not a tracing of a single action potential, but an amalgamation of the many action potentials that constitute the electrical activity of the heart.
Well, now we have very few time, so I have actually 2 more videos on this topic, and I recommend you to watch them. Now let me tell you a few words about your organizational process. So first let me send you some files. Oops. So I will send you some files. Okay, which is the file called some useful links. The next file is links to today's lecture, and the next file is topics for the test. Well, the very important thing I'd like to tell you is that I'm going to give you the first test in a week. So then at some time next week, you will see the test in your personal area on our website, and you will have about 1 week of time to pass this test. The test will contain 20 questions and 30 minutes for its passing. Actually, this test is not strongly required for passing the final exam, because you have a ranking system here, and you should get more than 51 rank. The rank should be larger than 51, but you can get it for doing exercises only. And even if you fail completely the first test, it is still possible to pass the final test. But the first test will be a training. It can be training for you, because the final test will look similar, but the list of topics will be increased. Today you have 25 topics, 25 equations. Most of the topics based on single equation. For example, Newton's second law, or Newton's laws. The questions will look like find acceleration if the force is equal to, for example, 4 newtons and mass is equal 2 kilograms. What is the acceleration? So your task will be to calculate based on simple formula some quantities, and for being able to pass the test, you should learn those formulas, about 15 or 20 formulas for the first test. They will be, most of questions will be written in form of questions with 4 answers. Well, you'll see it. If you have any questions, you can ask me at our university site. There is a place for messages. You can also contact me by Skype. My Skype login is PetaFMA. I'll send it to you. Yeah. So this is my Skype login, and you can write me at the email. Let's use this one. And it's links sent to you in this chat. So the file, some useful links. You can find the links to the videos with lectures. You can find the links. You can find the folder where all necessary files are stored. It is files with my PDF presentations. It is files with some PDF of laboratory exercises. For the moment, not every PDF are ready, but we will do it in a few days next. Well, mute someone, I don't know. Let me try to. PDF of this class is can be found at the same folder. In the same folder, it is already there. It is called lecture 5, and the other lectures is there. If you open the file, some useful links, then let me show you. Wait a second. Oops. So the file, some useful links. Let me open it. So this file, the first link is for our Zoom meeting. The second one is for Google Drive folder, and I'll open it for you on my Google Drive. So you can see laboratory exercises, lectures, questions, textbook, and questions for test also here. Links for all videos, so everything can be found here. And those who didn't write their names, please do it now, because well, I'm sorry, it shows in Zoom. In Skype, I thought it is in Zoom. Where is the let me change to the file.
Excuse me, doctor.
Yes.
Should we pass this test?
Yes, but the test is not the file. It will appear in your
In our site, university.
Yes.
Yes.
Right. And
Okay.
concerning your laboratory exercises, you should attach the report on your exercises. If you are doing exercises in laboratories, then the report can be just the photos of your notebooks with the data. If you are doing it online, then you probably know what to do. You have a PDF with data. You should fill empty cells in the tables and send it back in the form of PDF or Excel or some other form. So there are three laboratories, and that means we have three reports. One report for laboratory of mechanics, another for molecular physics, and another one for electricity. And those students who have missed some exercises, if you have a medical statement, then probably you don't need to do anything. But if you had some other reasons, you can do your exercises online instead of doing them in laboratory, because we have too few time for everyone. And we will give you the data and the task for home task for those exercises after the 1st of December, because now we are busy with other things. We need to prepare all the files with description of our laboratory exercises. When I say we, I mean there are 3 teachers and we all are busy with this. Well, now let us come back to my presentation. And once again, if you didn't write your name, please write it in the chat. It will be saved in a text file. I will be able to see who were present, who and who not. And one more thing. We had a well, you can see there are 2 playlists. The first one is the playlist with my lectures. For the moment, there are 4 lectures there, and today's lecture will be there in a few hours or in a few days. And this is playlist with laboratory exercises. For the moment, there are 4 exercises for laboratory of mechanics, and the home task is given for those exercises only for students who is studying online. Let me show you the links for today's lecture. We have seen 4 videos from this list, and there are 2 more videos which could be helpful for you, which is cardiac access in 5 minutes and basics of ECG in 5 minutes. I think it would be helpful for you, so you can watch them later. Well, and our time is over, so do you have any questions?
No, sir.
No, doctor.
Well, I see there are no questions. And once again, you can ask me questions by Skype, by email, and by our university site, the message for everyone. It will be seen for everyone.
Thank you, doctor.
Well, so see you again in 2 weeks, and be ready for the test in a week.
Okay,
So,
okay. Thank you.
goodbye.
Goodbye.
Well,